Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Modeling the Brain During the Industry 6.0 Era. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Velasquez, in 2021, published on SSRN, the paper Artificial Hypothalamus, Artificial Intelligence and Mathematical Programming Integration, in which the foundations of artificial brains, and more specifically of the hypothalamus, are laid. The article, and others later, carefully studies the relationships between the structures of the neocortex, with those formed when a mathematical problem is atomized, to use large-scale optimization methodologies, oriented to the partitioning and decomposition of systems, and they define the artificial brain in semi-detail. This is a disruptive vision of artificial intelligence, considering the power of computers, the evolution of mathematics, and the Internet of Things. This conference explains in a summarized way this evolution, based on the current state of AI. A complementary document is Artificial Brains, Augmented Artificial Intelligence, Artificial Neocortex plus Artificial Hypothalamus plus Artificial Hippocampus. Digital Industrial Revolutions. Today, the evolution of industrial revolutions is conceived as Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism, technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits, and resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability. Beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies, and ethical and conscious governance. AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. Are you ready for Industry 6.0? Artificial neural nets. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the article, A Logical Calculation of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to explain how the brain could produce highly complex patterns, by using many basic cells that are connected. Neural networks were growing, and in practice they took the name of artificial intelligence. They were also called machine learning. Neural networks have grown without paying attention to the structure of the brain's architecture, that is, how the main parts of the brain are connected, the cerebral cortex, the hypothalamus and the hippocampus, and the functions they fulfill. Neural networks developed as the fundamental element of communications within the brain, but without consider how they were connected, a lost component's fundamentals. At first, artificial neural networks were very small and gradually became GPT, in the hope of reaching AGI, which could be associated with a very large artificial neural network representing the entire brain, associated with many models, also very large, that with an infinite number of parameters would represent all the connectivity of the brain, ignoring the smart architecture of the brain. Given this lack of structure, we have a sum of neural network models that produce a supermodel whose networks come together in the brain, as if it were a Lego game in a backpack. The growth of artificial neural networks is due to the great growth of computational power, and not to a change in paradigm, which after 80 years should have occurred. It is to be expected that before the end of the Industry 4.0 era this change will take place. Artificial brains as a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. Now its concepts have been modified in the Industry 6.0 revolution. The science of decision-making using digital computers emerged in 1947 and can be attributed to George Dantzig. The AI in which artificial brains are located, He calls it artificial intelligence for decision-making. Dantzig's work gave rise to mathematical programming. Although mathematical programming is clearly a way to provide artificial intelligence to computers, and it grew much faster than the so-called artificial intelligence based on neural networks, to date mathematical programming is considered by almost all users, and by many scientists, as a methodology that is not part of artificial intelligence. There is no awareness that it is necessary for humanity, since its function is to optimize decisions. Mathematical programming has benefited from computational power, but not as much as artificial neural networks. This is due to the investment that humanity has made in GPT models. This indicates that in a new era, its power will play out, as it is much closer to helping achieve artificial general intelligence, AGI, a hypothetical type of highly autonomous artificial intelligence, that would match or exceed human capabilities in most, or all, economically valuable cognitive work. Artificial brains as a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. Artificial brains are an invention of high, due to their expertise in complex modeling. The image shows a close-up of the human brain showing the activation of neurons and neuronal extensions of the limbic system, mammillary pituitary gland, amygdala, thalamus, cingulate gyrus, corpus callosum, hypothalamus. This indicates that the human brain is composed of groups of neurons which in turn are composed of groups of lower-level neurons, or individual basic neurons, called by high the atoms of the system. The central idea of the artificial brain is to build an artificial intelligence that mimics the human brain, leaving aside the approach of trying to represent the entire brain using a single network of artificial neurons. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The hypothalamus is part of the thalamus. McCullough and Pitt's theory, which has existed for more than 80 years, has proven to be totally successful, and based on it the current state of artificial intelligence has been reached, which we could say are GPT methodologies. However, Velasquez-Bermudez's work, spanning 35 years of research and technological development, has resulted in artificial brains, which are a new way of thinking about artificial intelligence. Industry 6.0 and living industrial ecosystems. Smart grids, economic dispatch. The history. The first type of algorithm that solved the problem of economic dispatch was dynamic programming. Dynamic programming, DP, is a numerical technique for solving complex problems by breaking them down into simpler, overlapping subproblems, storing their solutions in tables, to avoid redundant calculations. The term programming in this context refers to mathematical optimization, not computer programming. The problems were faced as either deterministic or stochastic. Because it is numerical, there are many variations of the algorithms. Problems were solved based on a monolithic solution of the entire system. Taking advantage of the popularity of commercial algorithms, mathematical programming replaced numerical versions of dynamic programming. Problems were approached deterministically and solved based on a monolithic solution, implying a centralized approach. The realism limitations of deterministic mathematical programming was the starting point for incorporating large-scale optimization methodologies to solve stochastic programming problems. In these methodologies, Bender's theory and Lagrangian relaxation stand out. Conceptually, the two methodologies are similar. In general terms, problems are divided into two levels, the upper one related to the coordinating problem, and the second level with its slave problems associated with combinations of dimensions of decomposition. In the example, the subproblems are associated with the smart grids that must be coordinated. These methodologies are a solution method that allows parallelizing the problem and accelerates its solution time. However, the problem is solved monolithically, that means centralized. Smart grids, the Internet of Energy, and Industry 6.0 have brought about a fundamental shift in the mathematical approach to solving problems, giving rise to consensus algorithms to address the solution, as they do not require centralized solutions or human intervention. Consensus algorithms are essential protocols in distributed systems, like blockchain networks and smart grids, which allow multiple independent nodes to agree on a single state or value of truth. Its primary function is to ensure that the system operates consistently and securely, even if some components fail or act maliciously. In the case of smart grid optimization, the current solution is that each one acts autonomous and independent as a living industrial ecosystem, and together they solve the problems of economic dispatch or unit commitment. The rules of consensus are based on mathematical laws, such as the theory of duality. The consequence of this is to solve mathematical problems through artificial general intelligence. This vision, born of praxis, is becoming a new way of using mathematics. The structure of an artificial brain is made up of the artificial hypothalamus, hippocampus, and cortex, all of which perform functions like human equivalents. Artificial brains emulate the structure of the brain and use it to build the mathematical models. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The connection between all the subsystems, within and between them, is made by bioneurons. For this, biological neural networks are formed, through which information flows in the brain, and in general in the human body. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network, that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. This decentralized and autonomous way of acting is how the human brain operates and therefore must be imitated by any artificial brain. Each of these superorgans is made up of neuron networks, and lower-level superorgans. For example, the hippocampus has at least two functions and two areas, one that stores memory data and one that manages learning. This chain of organs and neural networks forms our brain. Artificial brains come from neuroscientific studies. The construction of the artificial cortex determines the connectivity of the artificial neurons, which are associated with the atoms of the system. In mathematical models, it is common to use a matrix that establishes the relationship between columns with variables and equations with rows. These matrices are scattered. This is the basis of cortical modeling. One of the scientists who has most influenced High's work is Jeff Hawkins through his publications, such as Why Does the Neocortex Have Layers and Columns? A Theory of Learning the 3D Structure of the World, and his book 1,000 of Brains, in which Hawkins presents a vision of artificial neural networks based on neuroscientific studies. High has integrated Hawkins' concepts into artificial brains. Emphasizing that High is not an expert in neuroscience, its interpretation of the functioning of the brain is presented. The cerebral cortex stores all the connectivity of the neural networks that make up the brain. It is the map of the brain. Artificial brains extend traditional artificial intelligence by generating decision-making artificial intelligence based on prescriptive analytics. The hypothalamus is a region of the brain that plays a crucial role in regulating essential bodily functions, including body temperature, hunger, thirst, sleep, mood, and hormone release. In addition, the hypothalamus helps maintain homeostasis, like the body's internal balance, through its connections with the autonomic nervous system and the endocrine system. It can be said that it is the motor of the brain. It is a vital structure for the harmonious functioning of the body, acting as a central control center for various physiological and behavioral functions. The hypothalamus is the organ that ensures the proper functioning of the human being. The connectivity of neurons in the cortex determines how the hypothalamus should function. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. The hippocampus is responsible for managing memory, which interacts with the hypothalamus, to determine the actions that the human being will perform, that is, decisions. Artificial entrepreneurial brains are based on these hypotheses. Today, the term human learning refers to the biological and psychological process by which human beings naturally acquire knowledge and direct learning via the neuroplasticity of the brain using technologies originating in Industry 4.0. Machine learning is a branch of artificial intelligence that allows computers to learn and improve their performance autonomously from data, without being programmed with explicit instructions for each task, uses algorithms to identify patterns, detect mathematical relationships, and generate accurate predictions about new information. Algorithm learning is the learning carried out by an algorithm, which participates in a machine learning process, so that the next time it can use information from the past, and if possible, improve performance. Neuroplasticity is the brain's ability to change its structure and functioning in response to new experiences, learning, and stimuli from the environment. Basically, learning is physically rewiring our brain. When you learn something new, neurons communicate with each other using electrical and chemical signals, or brain algorithms. If this activity is repeated frequently, the connections, synapses, are strengthened. If they are not used, weakened, or removed, synaptic pruning. This plasticity allows networking. Learning creates new neural pathways. For example, when learning a language, your brain maps new sounds and meanings. Constant adaptation. It is not something exclusive to childhood. Although it is maximum in the early years, the brain can change and learn throughout life. Compensation. If one area of the brain is damaged, as in a stroke, plasticity allows other areas to reorganize to take over lost functions. Direct learning driven by technology. Ray Kurzweil is a 78-year-old American inventor, writer, and futurist, widely known for his predictions on artificial intelligence and biotechnology. Currently, he serves as Director of Engineering at Google, where he leads natural language processing projects. Kurzweil predicts that humans will develop emotions and characteristics of greater complexity due to the connection of their brains with computers, and that by 2045, non-biological intelligence will be 1 billion times more potent than all current human intelligence, marking an irreversible singularity in civilization. On a commercial level, these services have been available for several years. For example, skull tomography, used to detect bleeding, tumors, fractures or brain injuries after an accident. Magnetic resonance imaging, ideal for accurate diagnosis of frequent headaches, providing pain-free high-resolution images. Brain ultrasound, generally focused on soft tissues and specific cases. What is new will be the public use of these technologies for the learning process of the human brain. Direct learning powered by nanotechnology. In the 2030s, human brains will connect to the cloud, allowing us to send emails and photos directly to the brain, and back up our thoughts and memories. This will be possible thanks to nanobots, small robots with DNA strands that swim in the capillaries of our brains. It will be just as the use of learning tools has been for human beings. The concept of learning through nanobots is at the intersection of advanced nanotechnology and neuroscience, posing a future in which knowledge will be transferred directly to the brain, or where our cognitive abilities will be artificially enhanced. There is currently research that lays the groundwork for this type of interface. Some examples are thought control. Prototypes of DNA nanobots controlled by human brain activity have been developed. In proofs of concept, a human operator has activated nanobots inside a living organism simply through cognitive effort. Neural nanorobots. MIT researchers are working on devices such as the Cell Rover, nanometer-scale antennas that can enter cells and transmit signals without damaging them, allowing precise electrical stimulation of individual neurons. Biological sensors. Nano-devices capable of monitoring biomarkers in real time, which will evolve into systems that detect cognitive fatigue or optimal learning states to intervene biologically. Donald Oldingham is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior in 1949. Hebb has been described as the father of neuropsychology and neural networks. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. Hebb's theory has shown that learning does not increase the number of neurons, but it does increase the connectivity between them. Donald Oldingham, July 22, 1904, August 20, 1985, was a Canadian psychologist who was influential in neuropsychology, where he sought to understand how the function of neurons contributed to psychological processes such as learning. He is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior, 1949. Hebb has been described as the father of neuropsychology and neural networks. His views on learning described behavior and thought in terms of brain function, explaining cognitive processes in terms of connections between neuron assemblies. Hebb concludes that the persistence, or repetition of a repetitive activity, or signal, tends to induce long-lasting cellular changes, which promote its stability. When an axon of a neuron A is close enough to excite a neuron B and repeatedly participates in its activation, processes of growth, or metabolic change, occur in one or both neurons, so that the efficiency of A to excite B increases. How do human brains learn? According to Hebb's theory, 1950, we learn if we form new synaptic connections between neurons. Learning is a new relationship that is created between neurons, and remembering is to keep that relationship socially active. When we are learning something new, neurons from different brain regions communicate with each other. With more exposure and practice over time, your brain creates stronger, more efficient communication between neurons. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. This principle suggests that the concurrence of neural activity is the basis for learning and memory. Synaptic strengthening: when a presynaptic neuron and a postsynaptic neuron are activated simultaneously, the connections between them are strengthened. Activity-dependent plasticity: the efficiency of synaptic connections is not static but can be modified as a function of neuronal activity. This plasticity is essential for adaptive learning and memory. According to High, the most important question Hebb solves is learning due to the addition of new cells in the brain? Learning is not about new cells, it is about new connections. Because of the creation of new and more efficient connections in the brain. Therefore, the learning process of an artificial brain involves increasing the number of connections that are mapped into the artificial cortex. This means larger and/or denser matrices. The stages of teaching and learning have occurred throughout the entire life of humanity, and they have been its means of development. Starting with human learning, in which humans teach humans, and humanity evolves slowly, this stage begins to change in the middle of the last century. Since the invention of computers, scientists begin the process of giving them the ability to solve real-life problems. This could be called the birth of machine learning, in which humans teach machines by making the algorithms that are the basis of artificial intelligence. This is the era we live in, which has the peculiarity that these algorithms are mass-produced and commercially sold to machine learning users. The next logical step is called by High algorithm learning. At this stage, machines will learn to create algorithms without human involvement, and algorithms will learn autonomously to improve their behavior. This is a necessary step to arrive at the artificial general intelligence, AGI, the dream of scientists. High is researching in High's algorithms learning as the next logical step to machine learning methods. Experience induces synaptic change. Synaptic change facilitates pattern competition. Activity, not synaptic change, is sufficient for memory cognition. From the point of view of High, one part of the artificial hippocampus processes the information stored in the other part, to develop a learning process. Learning takes the form of the generation of new neural connections, which must be stored in the artificial cerebral cortex, to be used in the future by the artificial hypothalamus. This high vision of artificial intelligence, built from the workings of the human brain, is currently unique in the world. Sparse analytics, or parallel and distributed analytics, is the methodological basis of artificial brains. High is the creator of the concept of artificial entrepreneurial brains, which is supported by the development of parallel thinking, when a complex system must be analyzed. The evolution of analytics, the mathematical science of analyzing and solving real-world problems, occurs in three directions. Productivity or speed of the technologies, complexity of the problems it can solve, and parallel thinking. On the other hand, there are three factors that are evolving and that allow the growth of analytics. Computing, which has evolved from monolithic to distributed processing, through parallel and dispersed processes. Types of analysis, which are classified as descriptive, predictive, prescriptive and cognitive, and mathematics, level of knowledge used, algebra, artificial intelligence, stochastic and robust mathematical programming and artificial brains. To be in the state-of-the-art of analytics, you need to work in the top-level row. There are two approaches to process data from a super measurement system that provides a non-enumerating amount of data, in real time and asynchronously, parallel analytics and distributed analytics. These two terms seem to be the same, but they are different and complementary terms. The parallelism and distribution of computing processing goes beyond the simple construction of parallel mathematical algorithms. It implies a way of facing problems with the bottom-up approach, from the description of atoms to integrating the vision of the entire system. It is a way of thinking about mathematics, according to the development of computer technologies. This is consistent with the abolition of monolithic computer applications, to make way for distributed applications based on microservices. Then the next step of advanced analytics is sparse analytics, which is based on parallel and distributed analytics. Asynchronous parallel analytics, called asynchronous parallel optimization by Velasquez, in 1995, 1997, and 1998, is defined as the act of solving a mathematical problem, using multiple cores on a computer, or on a computer grid, using modern multiprocessing environments, uniting the theories of decomposition and partition of large systems, that allow to structure complex multi-level mathematical models. Parallel analytics distributes workloads for data analysis, across multiple nodes in a server cluster, rather than addressing a large problem on a single supernode. The algorithms run on each node, processing a subset of the data. When processing is complete, or whenever required, datasets are aggregated, or rejoined, to generate collective information. There are many advantages of the asynchronous parallel approach. Less time to get information. By putting multiple nodes to work on the same problem, you can get insights from the data much more quickly than would be possible by running an analytics application on a single supernode with linear processing. This is a huge benefit when you want to get quick responses from massive amounts of data, and asynchronous processing allows to produce information that can be stored in memory until it is required by some subproblem. This speeds up the solution. In addition, it requires less demand for resources, avoiding congestion in computer systems. Distributed analytics is based on parallel analytics, and it is the distribution of the mathematical modeling process, in many agents that act simultaneous and independently, when they received information from its exogenous environment. The process can be summarized in the following steps. From a top-down process analysis, it is possible to construct mathematical or logical rules of interaction between multiple agents, representing each one a part of the system. Jointly, all the agents can represent the state of the reality. Starting from math, or logic rules, following an approach bottom-up, it is possible to build segmented, or atomized, models of the real world. Using asynchronous parallel processing, it is possible to define the simultaneous actions of all agents that keep on the right path a cyber-physical system. This processing is different from the traditional one, based on the synchronized use of mathematical models that are executed periodically. Autonomous real-time distributed optimization. Mathematically, this process may be supported by large-scale optimization algorithms, aimed at solving very large optimization mathematical problems, based on the intensive use of methodologies for partitioning and decomposition of systems. New technologies and big data shift from traditional optimization based on synchronized moments, to modern optimization, based on real-time events, in which models will run autonomously, when necessary, by events. Autonomous real-time distributed analytics is a topic open to researchers in advanced analytics. This evolution may be summarized as the shift from artificial intelligence to artificial general intelligence, that evolves from artificial intelligence very powerful in pattern recognition, to intelligence that powers the human brain, becoming an exobrain with high decision-making capacity, in real time, and autonomously. The decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. whose central organism simulates the board of directors. When all the models that make up a company are solved using the living organism concepts of Industry 6.0, the updated version of an artificial hypothalamus is obtained, and the board of directors is not necessary. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that controls the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence, to generate mathematical programming solutions, using the models that traditionally make up a decision support system. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. Human brains, a swarm of neurons. Industry 6.0, a swarm of algorithms of artificial intelligence. In 1962, the Dutch mathematician Jacques Benders published his theory of partitioning, which is a transcendental, not the first, step in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The author believes that Benders never perceived that the true importance of his research lay in the fact that he had established the way in which two algorithms would communicate with each other, and they could become a universal language for communicating a swarm of algorithms. If large-scale multi-level optimization methodologies, based on the partitioning and decomposition of systems, are applied to obtain the smallest atom of a dynamic stochastic model, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms, working autonomously and permanently, to achieve the goal proposed by the decision maker. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. Joseph Louis Lagrange was an Italian mathematician and astronomer, whose main idea is Lagrange multipliers, a strategy to find the local maxima and minima of a function subject to equality constraints, using the implicit function theorem. Lagrange's seminal idea is to convert a constrained problem into such a form that the theory of an unconstrained problem can still be applied. The principles of Lagrange theorists are still the support of optimization, but solving real problems using their techniques is no longer valid. Without knowing it, Lagrange generated the foundations of communication between cognitive robots, which speak mathematics as their natural language, allowing them to move like an artificial hypothalamus. RCADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information, you can consult the URL. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.